Alright guys, so in part 1, I finished chapter 1. In part 2, hopefully, I'll finish chapter 2. I'm not sure though, because it's pretty long. But I think I can skip the first few sections. I'm looking over them right now, and we we had them in grade 10, first of all, and then we had them 10,000 times in the Amazon homework. They're like, differentiate between distances and displacements. So if I'm talking about moving from A to B then to C, that means I displaced myself from A to C. My displacement denoted in delta x. So x is my position, right? Delta is a change. So a change in position is a displacement. This is equal to AC, okay? But the distance is different because I traveled from A to B, right? I traveled some length, then B to C, it's another length, right? So the distance in this case is the absolute value or the magnitude of AB plus absolute value or magnitude of BC. Okay, they're not the same. Sometimes they can be the same. Displacements and distances, they can be equal, but in general, they're not. Moving on. So we finished that. Let's talk about average velocity and average speed. We know that velocity, okay, average is equal to the displacement over a change in time, right? Now, how do I graphically interpret this? We have an xt graph. So this is t, this is x. Let's say my position changes like this, okay? And it moves indefinitely, I don't know, okay? My goal is to find the average velocity. So the velocity, that's the one thing you should know, okay? It's the slope of the xt graph. Whether you're talking about the average or instantaneous, I don't care. But they're the slopes, okay? Obviously they're different, but in general they're slopes. Instantaneous velocity is the slope of the tangent line. So if I take a point and I draw the tangent line through that point, the slope of the tangent line is the instantaneous velocity. However, if I take 2 points like that and I draw the secant line, the slope of the secant line is the average velocity, not the instantaneous. Okay, so this one is the instantaneous, this is the average. Okay, now how do I write that mathematically? So that's V average. V instantaneous, or just simply V, is equal to the limit as delta t goes to 0, right? Because I'm taking those 2 points, I'm taking those 2 points and I'm bringing this one really close to this one. If I bring it really close, then the 2 points will just be like 1 point and the slope will be like that, right? So this is also the instantaneous. Anyways, we have the limit as delta t goes to 0 of delta x over delta t. This is equal to the limit as delta t goes to 0 of the average velocity. Okay, so we finished average and instantaneous velocities. What about the speed? So I have the instantaneous speed is equal to the magnitude of the instantaneous velocity. This is true, okay? This is speed. However, the average speed is not the same as average velocity. The average speed average, is equal to the distance over the change in time, okay? That's why I have to talk about distances and displacements first. Anyways, so we have those 4 relations, you should know them. So let's do an example. So we have example 2.2, page 31. We have a body moves along a directed axis at a constant velocity. So the velocity is equal to 2.5 meters per second, right? At t equals to 0, the position of the body was 10 meters. So the position at t equals to 0, so it's a function of time, right? So the position at t equals to 0 is equal to 10 meters, right? Find the position of a body at t equals to 3 if the body is moving positive in the positive sense or in the negative sense. So A, we assume that v is positive, okay? That means that we have the equation of motion is x of t, so the function is equal to the initial plus velocity times time is also equal to like this. It's the same thing, okay? So substitute values, we have 10 plus 2.5t, right? So x of t is that. Now, they said t equals to 3 seconds, right? That means x of 3 is equal to 10 plus 3 times 2.5 is 7.5. Sorry, 7.5. This is equal to 17.5 meters. That's A. So B, we have the same thing except velocity is negative. That means x of t is equal to 10 minus 2.5 t. So that means x of 3 is equal to 10 minus 7.5, which is 2.5 meters. And we're done. Okay, moving on to acceleration. It's the same idea, okay? We had the velocity relationships over here. We have acceleration, average acceleration is equal to the change in velocity, average of course, over change in time, okay? And the instantaneous acceleration is equal to the limit as delta t approaches 0 of the average velocity over change in time is equal to the limit as delta t approaches 0 of the average acceleration. There's another thing that you should know, okay? The instantaneous velocity is the derivative of the position with respect to time, and the acceleration is the derivative of the velocity with respect to time. Those values are instantaneous, okay? We can also write acceleration is equal to the second derivative of x with respect to time. It's also correct, but I don't think you need to know it. This basically means that the velocity is the slope of the xt graph, and the acceleration is the slope of the vt graph, and inversely, we can say that the position, right, is equal to the area under the vt graph, and the that's the change in position, the displacements, and the velocity is equal to the area under the at graph. Alright, now comes the fun part. We will solve problems using uniformly accelerated rectilinear motion, so abbreviated UARM. Okay, this equation over here is URM. This is uniform rectilinear motion, right? That means there's no acceleration. In this case, we're dealing with motion with acceleration. That means we have a new set of equations. We have velocity with respect to time is equal to the initial velocity plus acceleration times time, right? And we have the position is equal to the initial position plus the initial velocity times time plus half at squared. Now, we can derive this equation from this one, because we know that up here, the velocity is the derivative of the position with respect to time, right? So it's the derivative of x0 plus v0t plus half at squared. Derive that to get v0 plus at. This is v of t is equal to v0 plus at, so we have derived this equation from this one. Anyways, those are the two equations. We have two more actually. Since we know that the displacement is the area under the vt graph, we have another equation. So we have the displacement, or the position, doesn't matter, is equal to the area under the vt graph is like this, okay, usually. And another equation is the v final squared is equal to v initial squared plus 2a delta x. Now, those four equations are really powerful. The first one, there is no displacement, right? The second one, there is no velocity. In the third one, there's no acceleration. In the fourth one, there's no time. Okay, so if we have an unknown, okay, and we don't have one of those values, we can choose the appropriate equation to use. So I'll do exercise 22, page 58. Okay, so a particle starts from a point A with velocity 3. So the initial velocity is 3 meters per second, right? And it moves with a constant acceleration, so acceleration is equal to 0.5 meters per second squared along a straight line AB, okay? It reaches B with a velocity of 5 meters per second. So V final is equal to 5 meters per second. We need to find displacement and the time. We want to find the displacement from the velocities and the acceleration. There is no time involved, right? So which one do we choose? We choose this one over here. So V final squared, so we have 5 squared, which is 25, is equal to V initial squared, which is 9, plus 2 times acceleration is 0.5, and then we have delta x, right? 25 minus 9 is 16, is equal to, well, 1 times delta x, so delta x is equal to 16 meters. Now, we want to find the time. We can use two equations over here. I'm gonna use the easier one, okay? So we know that the displacement is equal to the area under the VT graph, right? So we have V0 plus V over 2 times time, right? This is 16 is equal to 3 plus 5 over 2 times time. So we have 16 is equal to 8 over 2, 4 times time. So time is equal to 4 seconds. Okay, now we start free fall. I'll do it by an example, okay? So, exercise actually. Exercise 29, page 63. Let's see. A stone is thrown straight up with an initial speed of 8 meters per second from a roof of a house that is 7.2 meters above the ground. Let's draw it first, okay? So we have the building, and here's the ground, okay? We know that the height is 7.2 meters. So the height is equal to 7.2 meters, and it's this distance over here, right? And then we have a ball like this. It is thrown straight up, and then of course it will go down, right? It will fall down. So straight up and then down. Okay, we'll assume that the ball will miss the building and actually fall all the way down. So there is a maximum height that it reaches, right? And then it hits the ground with some velocity, right? So part A, they ask us the speed with which the stone hits the ground. So we need to find the velocity, then the speed. Okay, the speed is just the magnitude, right? The time which elapses, so part B is the time which elapses from the moment when a stone is released until the stone hits the ground. Okay, so how do we do it? We know that the initial velocity, we have the initial velocity is upwards, right, is equal to 8 meters per second. We'll choose the positive sense, we'll choose the positive sense being upwards, okay? That means the initial velocity is positive, the final velocity should be negative, and the height is positive. How do we do it? Now, notice that we're in free fall. The acceleration that we experience is the force of gravity, right? And what's the gravitational field strength? G is equal to 9.8 meters per second squared. Now, is it pointing upwards or downwards? Now, downwards, right? That means the acceleration is equal to negative g because we chose our positive being upwards. So, this is equal to negative 9.8 meters per second squared. I'll say it's about minus 10, okay, to simplify my calculations. So, what do? We want to find the V final, right? So, V final, we know a relationship. We know that V final is equal to, V final squared is equal to V initial squared plus 2a delta x, right? What's V initial squared? We have 8, which is 64, plus 2 times, what's acceleration? It's negative 10, right? What's delta x? It starts from here. Look, it starts at this level, right? It goes down to this level. So the change in position is negative. It's negative 7.2. Even though the height is 7.2, but you move downwards, right, from up to down. Let's see. So this is equal to 64 plus 20 times 7.2, and then so this is V final, right? V final squared. That means V final is equal to the square root of 64 plus 144, I think, 208, which is about 14.3 meter per second, right? So that's v final, right? But we know that the velocity, the vector v final is equal to negative 14.3 meters per second because it's going downwards. But of course, the speed is positive, so that's the speed. Now for part B. So that was part A. Part B. Let's see. Find the time which elapses from the moment when the stone is released until the stone hits the ground. So, when does it hit the ground? It's when the position is 0, right? So, we have the position, which is x of t is equal to, let's see, this is x0 plus v0t plus half at squared, right? What's x0? Is the initial height, right? Which is 7.2 plus what's v0? It's at, and then we have a minus 5t squared. Minus 5 because we have a half a. What's a? A is negative 10, right? So we have negative 5 over here. Anyways, so what's x of t? It's 0, right? We want it to be 0 because we want the time where it hits the ground. When hitting the ground means that its position is 0. Let's see. So we have 5t squared minus 8t minus 7.2 is equal to 0. So I'll solve the quadratic equation. I'll get t is approximately equal to, let's see, 2.28 seconds. And then we have another t which is equal to negative something. So don't take the negative, of course. Actually, I think my values are... Because look, I chose my acceleration is equal to negative 10, right? When I was solving it, I chose it to be negative 9.8. So the values might be a little bit different if you chose 9.8, 9.8 or 10, but they'll specify that in the exam, okay? So if you were solving this and you were seeing I got 2.28 and you got 2.26, for example, don't worry, it's just a small error, doesn't matter. Okay, so we're in the last topic, which is relative velocity. I think this is best explained through an example. So we do example 2.15, page 65. John cycles north at 20 kilometers per hour with respect to the ground. So my coordinate axis, this is 20 up, right? And then Kate cycles to the north at 25. So this is John, and then Kate is like that. Okay, that is Kate. Find the velocity of Kate with respect to John. So I'm John, okay, and I see Kate running. Now she's faster than me, right? I mean, not running, cycling. She's cycling faster than I am, right? So I'll see her velocity being positive. I'm assuming that the positive is upwards, okay? This is positive y. Now, myself, I am also moving, right? I'm moving at 20 kilometers per hour, but Kate's moving at 25. That means she's moving faster by 5 kilometers per hour, right? That means the velocity of Kate with respect to me, which is John, is equal to 5 kilometers per hour. And that's it. Now, what if Kate was cycling in the other direction? So, like this. Let's say 5 kilometers per hour towards the south direction. So that's K. That is, so we have 20 here, and then we have 5 here, okay? What is the velocity of Kate with respect to John? Now, I'm moving 20 up, right? Now, Kate is moving 5 down. That means I will see her as if she's moving 25 towards south, right? Towards the southern direction. That means the velocity of Kate with respect to John is equal to negative 25 kilometers per hour.